So we have seen different types of branch predictors, the tournament predictor, the global predictor, or what we now call it as a correlation predictor. Okay. It's also called a correlation predictor because we are trying to correlate the behavior of one branch with some other branch. And of course we also saw the k-bit predictor. We saw 1 bit, 2 bit, 3 bit, and then we also mentioned that a k-bit predictor, k greater than 2, is as good as a 2-bit predictor. And so many of these predictors, still the Bible is Hennessy and Patterson computer architecture book, and you will see this plus many more predictors you can search. You will get close to 500,000 hit when you say branch predictors in Google. Okay. So with this I will sign off on this, and this is what I believe that you should know in some amount of detail. Of course when you go to an advanced course in computer architecture, you will learn how a tournament predictor can be implemented, right. As you see, a tournament predictor is one which will move from, depending on the behavior of a branch, I will move from one to next to next to next. And so the branch predictor actually starts becoming intelligence, right. So there is a machine intelligence that is built there, okay. So it will intelligently predict branches, okay. So there are very fundamental questions. Can a tool which will enhance the intelligence of a branch predictor have branches inside it, and so on? Okay. So very interesting questions that we can try and handle. Okay. So with this, there is a scope for a lot of intelligence to be built, and a lot more scope for writing papers. So that is where we stop here. Now we move to the next type of hazard. So we have seen data hazards, we have seen control hazards, we have seen some remedies for each one of them, correct. And importantly, do remember the 0 cycle instruction. Okay. So it's very, very important. Now let us go to the last type of hazard in a pipeline, which we call as a structural hazard. See, the structural hazard is something like, see, we have some multiple functional units. Each of these units will not do everything, right. There is no point in keeping, say for example, there is no point in having a load store functionality inside an adder unit, right. So I can't have one unit which has both load store and add, or load store, add and floating point, right, because if I have such type of units, then I will be wasting a lot of space. And we cannot also selectively go and disable parts of that unit in some sense, right. There will be a lot of dependencies. So what will happen is, I will not doing any floating point operations, summa I will be wasting power, I will be hanging around. So I will put lot of area, and also I will be wasting power there, because if I have all the things in one execution unit and you have multiple such execution unit, we will say these are all symmetric execution units, right. Then what will happen is that either I will be doing some floating point operation, or I will be doing load store, or I will be doing integer arithmetic, but not all the three in the same unit. So if when we look at multiple execution unit, which forms the basis of course the superscalar architecture, there will be some execution units will do integer arithmetic, some execution integer and logic arithmetic, bitwise and bitwise or sort of things. Some will be dedicated to do floating point, some will be dedicated to do load, and some will be dedicated to do store. Now if I get, suppose I am getting those 6 instructions as we saw in the previous example, right. We have seen that 6 instructions that we saw here. These 6 instructions are such that all are store or all are load, for example, the worst case, and I have only 2 load units. The remaining 4 instructions have to wait. This waiting is not because of a control issue, it is not because of any data issue, it is because of the non-availability of the functional unit. It is because the structure of the architecture does not have enough units to do this computation, and that is why we call this as a structural hazard. Okay. So what it means to build this architecture, there are a lot of questions here to answer. How many such integer instructions I will get at any point of time? If I am going to get always say 5 to 6 integer instructions which can execute in parallel, then to actually get the bigger speed up, I'll put the 6 integer execution units, right. If I am only going to get 3 or 4, then the remaining 2 I will not put. By that I will reduce my power consumption, etc. So today when somebody wants to buy your architecture, first thing they will see how fast is your architecture. Second thing, they will also come and see how much power it is going to spend, it's going to consume, how much area it's going to consume, how much heat it is going to generate. All these things also now start coming up when people try to build by your architecture, specifically in a high performance computing type of environment. We are looking all this superscalar more from a performance point of view. So what should be, see in this case as we see here, we have actually assumed that all these units are symmetric. All these units can execute every instruction, but that will not be ideally the case, right? And that is where we land up with what we call as the structural hazard. I will just read out the red statements here. Non-availability of a functional unit will cause this structural hazard. Say I would like to schedule the 7th instruction in our example. There are only 6 units, that is also one of the symptoms. The new instruction has to wait. And then ideally we will have separate integer, floating point unit and load store units. And so in a load store architecture, of course you know what a load store architecture is. Now when there are a lot of load instructions, then it will not, there can be a potential functional hazard. Now the next step, right, what it means to do compiler fine tuning for an architecture, right, fine tune the program for your architecture. It will see that for this architecture there are only 4 integer units, right. So it will, if there are 2 floating point instructions far off, right. So I have, say let us say I have 4 integer instructions, then so suppose I have a lot of integer instructions and some 2 floating point instructions here. So I say I1, I2, I3, I4, I5, I6, I7, I8, I9, and these 2 are floating point instructions. They are I8 and I9 are dependent on each other. Of course these are all I1 to I4 are independent, I5 to I7 are independent, let us say, or I1 to I. So suppose there are 4 integer units and 1 floating point unit in your architecture. What I can do is I can push this I8 here and send this together, because then this 4 will be fetched along with I8, and so, right, rather than this I5 going and it has no units and it will start waiting. When it starts waiting, everything else has to wait in the program header, because the computer doesn't, the system doesn't know that, you know, because all these things, all the instructions are waiting, now all the subsequent instruction has to wait. It can't now go and schedule I5, I6, I7 etc., because there is no functional unit, there is no reservation station, right. So if at all somebody has to wait, it has to wait on the reservation station. So I8 there is no, I5 there is no reservation station, because there are 4 integer units and I5 is also in integer instructions. But there is a floating point unit. So what the compiler can do is it can push this I8 along with this, so that when the hardware fetches, it will fetch these 4 integer instruction and 1 floating point instruction, and that can start executing on this. In the next step it can bring these 3 integer instruction along with this floating point instruction, correct. Otherwise what will happen, I1 to I4 one has to finish, then I5, then I6, then I7, then I8 alone will go, then I9 will go, because there is only 1 floating point unit. Are you able to understand this? So by doing this type of execution, by doing this type of what we call as a code motion, where I move the code from I move an instruction from one part to the another. By doing this rearrangement, the compiler can ensure that the finally, this is a dynamically scheduled process, but it can effectively use this. Understanding? So even for a dynamically scheduled superscalar processor, there are some tidbits which the compiler can do in order to improve the performance. Okay. So this is what we understand by structural hazard. We will talk about one more structural hazard as we move down with memory management, right, at that point of time. But as far as execution goes, this is what we mean by structural hazard, and this is what the compiler can do to handle structural hazards. Now with this is all about superscalar pipelining stuff, okay, and all that we have discussed is now over. Now what we will do is, now we will start talking about more on more deeper into the architecture. I'll cover this Amdahl's law, which is very, very important, and then we'll start talking about multi-core architectures. Okay, that is what we will do till we touch quiz 2. Post quiz 2 we'll look at cache memory and organization, cache and IO. Okay. So any doubts in pipelining, superscalar? Shall I proceed? Yes. Okay. Shall? Can you go? Can you go ahead? Okay. Now comes to this Amdahl's law. See, Amdahl's law is something that an architect, it's a tool for the computer architect. See, I want to do some enhancement. See, I am not satisfied with the performance. I want to do some enhancement to improve my performance, right? Now I need some guidance for doing this enhancement, and that is what precisely Amdahl's law basically talk about. Okay. See, so Amdahl's law basically quantifies something called speed up. We are only talking about performance here, no area, no power. Okay, we are talking about performance here. Amdahl's law talks about what is speed up. Speed up is defined as the execution time without enhancement divided by the execution time with enhancement. The time should decrease, so the speed up should always be greater than 1, correct? So the speed up, this parameter is defined as execution time without enhancement divided by execution time with enhancement. The execution time without enhancement, whatever enhancement that we are talking of, will be greater than the execution time with hopefully greater than the execution time with enhancement, and hence we will get a better speed up. So Amdahl's laws helps you quantify the speed up, right? I go and say I want to do this enhancement, then you will ask what would be the speed up, right? That's even a colloquially you will ask, oh okay, go and do this, what will be the speed up? How fast will the computer run in contrast or in comparison to what it is currently? What would be the enhancement in speed? And that is what we are talking of. So so we will be trying to get some very good expression for speed up. Now what will happen in an enhancement? When I enhance speed up, how do you compute the speed up? We run benchmark programs and we compute the speed up. We ran benchmark programs on a model without enhancement, we get some total number of cycles. We now run the same thing with enhancement, we will get a new total number of cycles. We divide one by another, and that is what we call a speed up. Now when I want to do this enhancement, it will not be that the entire program gets, every instruction of that program starts working faster. For example, my enhancement would be on the floating point. So that means the floating point instructions alone will start working faster, right? So when I do an enhancement in the architecture, it is not that every part of the program gets enhanced, a fraction of a program will get enhanced. For example, in my executable, if I have say 10 floating point instructions out of 100, say 10%, and I improve the floating point performance, that means those 10% or 0.1 fraction will improve, right? Able to comprehend this, right? So see, every book just gives this law and proves it, but you should say what is the justification of having such a law. See, there will be several ways by which I can estimate speed up. Why should I estimate it in this fashion? Why should I have these type of A? That all these whys are not answered, so please note it down very carefully. A actually stands, this A actually stands for the fraction of computation time in the original architecture that can be converted to take advantage of this enhancement. Fraction of computation time. There are 10% of the time. Why this definition? It is not just fraction of the instructions. Fraction of the instruction will not make any sense, right? I would have only 3 instructions, but the 3 instructions will run 1 million times. So so there is the 10-20, 10-8, 10-90 rule, right? 90% of the code will execute only for 10% of the time. 10% of the code will execute for 90% of the time. So if suppose I have three floating point instructions and 10 integer 9 integer instructions, okay, so totally 12 instructions. So what is 3 out of 12? 25%. If I go and improve the floating point performance, I say that 25% there will be improvement. It's a wrong statement. Suppose these 3 floating point instruction, these 12 instructions execute for say 100 units of time, and this floating point instruction itself consumes 90% of the time, right? If I improve the floating point performance, the performance of your code will increase much more than that 25%. Okay. Suppose these 3 floating point instructions only consume 3 units of time out of 100, and I go and improve this floating point, nothing will happen, because the majority of the time is spent on still your untouched instructions. Okay. So when I am trying to model this A, it is more appropriate for me to model A as a fraction of computation time rather than a fraction of the number of instructions. Are you able to get this? Any doubts? Are you able to follow? Why should A be fraction of computation time and not fraction of instructions, as I just told a bit earlier? Are you able to get the feel? Yes or no? Okay. So what is the new execution time? Execution time of the new code is nothing but 1 minus A times the execution time of old, because A% of that code is only enhanced. So the remaining 1 minus A portion will remain the same. So 1 minus A times execution time old, right, plus the execution time of the enhanced portion, right, because A% of the time is now enhanced, and that is accounted for, A% of the code is enhanced, A% of that execution time is enhanced, and that is accounted for here, while the remaining 1 minus A is still the old code. So that is 1 minus A times execution. So if say 0.4, so totally I am taking say some 10 seconds, right, and 0.4% of your program is now enhanced, remaining 0.6 into 10 seconds. The remaining 0.4 means that 4 seconds of my running time is now improved. The remaining 6 seconds will remain 6 seconds, and that is what this 0.6 into 10. That 4 seconds, 0.4 of this 10 second is improved to say 2 seconds, so the total time now becomes 8 seconds. Is it okay? Are you able to follow? So the new execution time, if I say 0.4, the original old execution time was 10 seconds, this is 10. 0.4% is the fraction of computation time which is taking the advantage. That means there will be some instructions executing for 4 seconds, those instructions are now enhanced. The remaining 6 seconds will remain 6 seconds, because the remaining 0.6 has to remain. So that 0.6 into 10, this 6 seconds is accounted for here. Now the remaining 4 seconds for which I have done an enhancement, that 4 second has now become 2 seconds. So the new execution time will be 8 seconds. So the speed up now will be 10 by 8. What is 10 by 8? 1.25, correct? So okay?
So does this not depend on the program execution time without enhancement upon with enhancement? For different programs this ratio can be different, right?
Yeah, that's always there. So we are only talking about some benchmark programs. So see, we can't actually measure for all the programs on it. So that's why that benchmarks have come. So we will run all the spec benchmark, for example, SPEC, and for that we will get the speed up. So speed up, it will be respect to some benchmark, set of benchmark. On a whole, this benchmark performance is improved, so I can go and sell it in the high performance computing server market. When I want to go and compete in the server market, people only will look at this type of execution time. So I can go and sell it in the server market if my thing improves. This is what it is. So we will do this for one class of benchmarks, spec benchmarks. I have already asked you to go and look at benchmarks, right? So this is any doubt? So let us keep this in mind. Execution time new is 1 minus A times execution old plus execution time of the enhanced portion, and the overall speed up is execution time without enhancement divided by execution time with enhancement, and A is the fraction of computation time in the original architecture that can be converted to take advantage of the enhancement. Okay. Now what is speed up enhanced? Speed up of the enhanced portion of your code. The speed up of the enhanced portion of your code is nothing but the execution time of the enhanced portion old divided by execution time of the enhanced portion new, correct? The speed up of the enhanced portion alone is nothing but execution time of the enhanced portion old divided by execution time of the enhanced portion new. The execution time of enhanced portion old is nothing but A into execution time old, because A% of the time is what I am getting the enhancement for. So execution time of enhanced portion old is nothing but A into execution time of old. So the execution time of enhanced portion new is nothing but A into execution time old divided by speed up enhanced. Substituting back in 1, what? I am going to substitute this execution time of enhanced portion. So the execution time of enhanced portion is A into execution time old by divided by speed up. Okay. So the execution time new will be 1 minus A into execution time old plus A times execution time old by speed up enhanced. So execution time new is equal to 1 minus A times execution time old, 1 minus A times execution time old plus A times execution time old by speed up enhanced. So what is overall speed up? Execution time new divided by execution time old is nothing but, execution time old divided by execution time new is nothing but 1 by 1 minus A plus A by speed up enhanced, right? Just take this, please take this derivation. This is a very simple derivation of Amdahl's law. Please copy this and then we will go and find out why this type, why am I interested in this form. Have you all copied? Now can you tell me, Palghat and IIT Madras, can you tell me why do I need a formula like this when I want to calculate the overall speed up? But that overall speed up has something called A and something called speed up enhanced and nothing more. It could have had other things, right? It could have had execution time of enhanced portion. There are so many variables that we have seen. Why am I interested just in A and speed up enhanced? Why should I get a formula like this and not something else? I could have got different varieties of formulas, right? Why am I interested in this form? Speed up overall is equal to 1 by 1 minus A plus A by speed up enhanced. Meaning?
If we change something, how will the overall speed?
No, that's what we are trying to calculate. And in the process of calculation, I am just landing up with this form. This is the formula that I am using now for this, right? This is the formula I am using. Why in this form? Why not in something else? I could have derived other ways of the speed up overall. We have n different forms.
You can compare which portion of the...
Why this form?
This data is already available to...
Availability of data, excellent. Okay, see, A is available to me, right? Because I can run the benchmark. When I run the benchmark, there is something called the execution trace. Right? When I run the benchmark, I can know every instruction how many times it is executed. And when I do an enhancement, I know which are all the instructions I am touching. From that I can go and find out, and I know for every instruction how many cycles it will take. I know how much total cycle the program took. From that I can actually compute A accurately. Correct? Then next thing, I go and improve some performance speed of some part. I can really find out what is the speed up there for that part alone. So my speed up enhanced and A can be accurately computed. That is why I would love to express my speed up overall in terms of A and speed up enhanced, because these are the things that I could compute with lot more accuracy. I have a model, I know I can run the entire spec benchmark on instruction set simulator, and actually I can go and find out every instruction how many times it is executed. And I know what is the total length of this program, total number of cycles consumed, not the length, it is the number of cycles consumed by this program. And when I go and touch some enhancement, I know which are all the instructions that are going to get affected. From that I can basically get this A. A is the fraction of the computation time that is affected by this. So I can get this A very quickly. Similarly, I could also get the speed up enhanced because I work on that model, so I know the previous model, now I have gone and improved on that model. Now for me to get speed up enhanced alone is very easy. So by this, I can basically find out whether there will be speed up or not. So let us take some examples before we end up today's class. So let us take a program which always takes 50% FP operations, in which 20% are FP square root and 30% are others. So I am taking a benchmark scenario where always any program I will have 50% floating point operations. Let us assume it's a highly scientific computer, and in that 50% of FP operations, 20% of it will be square root and 30% will be some other instructions. Now this is the scenario, this is the program that is given to you, the assembly program that is given to you, and you have to now start executing an architecture, arrive at an architecture which will handle these classes of assembly program very nicely. So you are given two choices: use a hardware and improve floating point square root to get speed up of 10. Right? This floating point square root currently is implemented in the instruction set. Now can I go and improve the floating point square root to get a speed up of 10? This is a question. Suppose that's a way, I put it as choice 1. Choice 2 is use software and improve all floating point operations by a speed up of 1.6. Don't bother about all these floating point hardware, we will give you software which will go and improve all the floating point operations by a speed up of 1.6. So what is the speed up in choice 1? 1 by 1 minus 0.2 plus 0.2 by 10, right? Because 20% is floating point square root. So in an overall program, the A is 0.2, right? So 1 by 1 minus 0.2 plus 0.2 by 10. So this is because I need a speed up of enhanced of 10. So the speed up in choice 1 is 1.22. Interestingly, the speed up in choice 2 is 1.23. So if I really want to enhance, then I'll prefer choice 2. Not only that it is not a hardware, it can be done in your lab, it's just software and compilation, but interestingly you find that the software solution gives you much better, much better, almost equivalent but slightly more better speed up than the pure hardware solution. Okay, so just to wind up, so we had given two choices. One choice was that I will go and improve 20% of this square root, 20% of my runtime I will improve, but then the speed up would be 10 times. The other was that 50% of the time I will improve by the speed up by a speed up of 1.6 for that portion alone. Now when we see that the choice 2 becomes much more favorable than choice 1, and choice 2 is also important because I can go and do everything in software, I need not touch the hardware. So this is much more simpler, we will talk in lakhs of rupees, while here I will lakhs of Indian rupees, while here I am talking of millions of USD. Okay, so that's the difference, right? So please understand. So Amdahl's life, if you just look at it to start with initially, if I had asked this question before teaching Amdahl's law, I say floating point square root takes a lot of time, I will get a speed up of 10. It is taking 120 cycles and I will make it 12 cycles or something like that if I say. Then we would have actually gone and fallen in prey for this choice 1. But then if I use choice 2, I save a lot of money and I also get better performance, at least 0.01 more than this, right? Okay. If the program runs for 10 hours, right, 0.01 essentially is a very significant time. If the program runs for 10 days, some simulations run, then 0.01 is some 2.5 hours. Okay, so it actually means quite a large amount of time in terms of this. We will now go in the next class, we will now go into the multi-core. So whatever I have talked so far is about a single core. Now we need to enhance it for multiple cores, and the systems that you are going to use are multi-core systems. So whatever you have learnt here will become extremely useless if you don't understand the multi-core architecture. All the superscalar will be one core, like that many things will be put, and what it means to arrive at that bigger architecture, and that we need to understand because we don't find unicore machines anymore. Okay, everything is multi-core. Your phone has 8 cores or will have 8 cores. Currently it will have 4 cores and it will have 8 cores. So even when you want to understand how your mobile phone works, somebody can ask you this question of how your phone works. You should be in a position to answer those questions. So we will talk about, so the next joke comes in what we call as the cache coherency protocol. So now we will teach some rudimentary, simple but working protocol. Then people have started working on it. Some 100 protocols have come just handling cache. Okay, so but we will see some interesting things in that, some real salient things that we will cover there also. Okay, thanks.